Thanks a lot for this great introduction. Yeah, today I want to give a short overview about our typical workflows of how we develop computational models with SBML. Yeah, this work is mainly funded by the BMBF and the DFG. Yeah, so we're mainly interested in computational modeling of the liver, and this is important for diagnostics, like for instance of liver disease, but also for monitoring disease progression and interventions. What we're normally interested in is something which is called functional capacity of the liver, and this is like basically how much the liver can still perform a certain metabolic functions. And this is especially important in the context of hepatectomies or in liver transplantation. What is normally done to evaluate such liver function is so-called dynamical liver function tests. And you basically give a certain test substance, which is then specifically cleared by the liver. And you can then use the rate of disappearance of the substance or rate of appearance of a product as a proxy of the actual liver function. There are a ton of test substances, and Indocyanine, green, caffeine, galactose, Pravastatin, dextromethorphan, and so on. But because the liver is the main organ of detoxification, you could basically almost any drug you take, the liver is one of the main organs involved in the detoxification. So this is not only important for liver function, but it's also important for detoxification of substances. Key important problem with this dynamic liver function test, or general, like I would say clinical test, is the very large intra-individual variability. So it's part of this decaying curve is due to the liver function, but many other factors can influence how this curve looks, like for instance, anthropometric factors, lifestyle factors, genetics, and so on. Yeah, so I will give short examples of computational models which we develop in this domain, and then I will give a bit more practical introduction of how we use the tools and how we use SBML to actually create such models. One example we developed was Indocyanine green liver function tests. We were interested in factors such as anthropometric factors, like how is age or age, weight, or sex affecting this test. Yeah, what we normally do is building so-called physiological based pharmacokinetic models. These are ODE-based compartment models which connect the different organs via the blood flow, and then you put, I would say, submodels or tissue models in the different tissues which are of interest for the substance. Most of the time, we're interested in the liver. Often also the kidneys are involved, or muscles, and so on. And so we basically have this whole body model and then couple it to tissue models of the liver function. Like in the simple example, this indocyanine green is just taken up in the liver. It's then directly exported in the bile. And from the bile, it can then be transported in the feces. So there's not much metabolism. There's basically transport. But this transport rate depends on many things, for instance, liver volumes, liver perfusion, but also like amount of this transporter proteins. Yeah, such models allow to answer a lot of interesting questions. For instance, you can apply them to ask, okay, how is liver function changing in liver disease, such as cirrhosis, or you can also look at medical interventions, such as resections. Most of the time, this is just this simulating certain applications is just mapping this application to certain parameter changes, and then you simulate the model with this changed parameters. For instance, resection, you can imagine this is basically a change of actual liver volume, and in the model, you just reduce your liver volume and basically do an in silico hepatectomy and then compare the model predictions with the data. Yeah. Other questions we are interested in is like interactions between liver functions and kidney function. Here we developed a model for Pravastatin, which is one of the main statins. And the metabolization is not only affected by liver function, for instance, cirrhosis, but also by the kidney function. And we were then interested in, okay, how does this play together? Because often patients who have kidney problems also have liver problems and vice versa. And So we were interested in the interaction between the diseases. Yeah. In addition, we often look at genetic variants and how these can affect the liver function or metabolic function. And most of the time, this is just changing the activities of the proteins which are involved in the in these reactions. Like here, for instance, we're interested in this ORTP transporters or the MRP transporters. Okay. A third example of such a model is it's often very similar. You just change different proteins, you change different, you add different components to these models, and then you simulate your question. Like with the dextromethorphan, we were mainly interested in the effect of the CYP2D6 genotype. The CYPs are the cytochromes P450, and they are key enzymes in the metabolization of drugs. And for certain of these isoforms of the cytochromes, there are genetic polymorphisms which can strongly affect the function. And then depending on what genetic variant you have, you can be either like a poor metabolizer of the substances or an intermediate, extensive, or ultra rapid metabolizer. This normally there are different activity scores, and then yeah, we simulated this different activity scores and distribution activities of activity scores in the typical populations and in different subpopulations, and could basically show by a very simple simple mixture model that we can very well reproduce like population effects and changes in different populations and so on. Yeah, in the end, this is, I would say, if you have a model which you can change very easily, and then a lot of these questions can be studied easily in silico. And so most of the time, what we do is encoding the models in SBML and then change parameters to study certain questions. For instance, for the activity score here, we changed basically, we basically have a parameter which is for the activity score in the model, and then we can just vary it and build basically, depending on the two genetic variants the subjects have, we can build basically the coupled genetic variant and then simulate the phenotype. Yeah. Underlying all these models all these models are basically encoded in SBML, and this has nice advantages. Basically, we have ODE-based models, and these are what we're doing is basically process-based ODE models. Our processes are mainly transport reactions and metabolic reactions in the different tissues, and a lot of blood flow transport or other reactions which correspond to physiological processes. For instance, urinary excretion of substances, like some substances go over the breath. So we have like a reaction or like a process which is saying how fast the substance is leaving the breath. It has a big advantage to use SBML. First, we have like a reproducible exchangeable model encoding. Secondly, we have access then to high performance simulator and are sure that our simulations are correct. Especially LibRoadrunner allows us to run many of these simulations. You can imagine, like, if we simulate here populations and have to sample like 1,000 of times from the different activity scores, this takes a lot of time. And if you do this then for 10 different populations and so on, and you have to run a lot of simulations, and this has to be fast. And by having SBML and LibRoadrunner, this can basically be done in a reasonable time frame. We can annotate our models, which is very nice, so that we can directly document what we're doing in our models and what the objects are standing for. For us, very important is a hierarchical model composition, because we basically build our models by having comp models, one model for the whole body physiology, which is connecting all the tissues. And then we have separate tissue models, which couple and build basically a hierarchical model of tissues and the whole body model. This is very nice because we can test this tissue models in isolation, and they are small and can be errors are easily found. And then we have also like standardized script to say, okay, we have tissue models and want to couple them with the whole body physiology. So there's a lot of reuse between these models, and basically the whole body physiology is not changing, just the metabolic or process models which we put into the whole body are changing. Yeah. Other things which are important as far as a lot of unit checking, distributions. You saw already a few of this distributions in activity scores and so on. So often we have the underlying distributions of parameters, and we can encode them with distrib. And yeah, we can use a wide range of tools to perform our models, to work with our models. Yeah, one tool which we especially use for the model building is sbmlutils. It's a package which allows to create and manipulate SBML in Python. And we basically use this for having programmatic way to create our models and to couple our models. Yeah, there are a few new features since the last release. Now we have also antimony model import, which is I think very nice. So we can import the antimony models to our internal model structure and then just reuse it. So things like, okay, just writing a simple tissue model in antimony and then couple it to the whole body model is now much easier. Yeah, also model merging and things like that is has been improved, and we have now support for the new FPC version 3 package. Yeah, normally we create the objects in the model as an instant of the SBML objects, and then this information can later on be visualized in different tools. Yeah. The second tool we're using is basically SBML for humans. This is an interactive report which allows to inspect the SBML content. So we create the model with sbmlutils, and this is the model report which allows us to check things or to communicate things, mainly also with our cooperation partners. Yeah, this is a web application where you can upload your SBML models, and it renders the information in the SBML and the metadata and so on. And yeah, for us also interesting, it allows like a simple integration with URL endpoints, which is nice for communicating models. But I will show an example in a second. The last tool we use in the model creation process is basically the Sci3 SBML. This is a cytoscape network visualization app, which allows us to visualize our networks while we create them. And so normally, like I would say, that we're doing an iterative model building using these three tools: sbmlutils, Sci3 SBML, and the SBML for humans, plus some additional tools like, for instance, antimony, and of course then later on simulators like libroadrunner, Copasi, and so on. But having the SBML as a main exchange format, we can easily use these different tools in our workflows. For instance, also things like parameter fitting with Amici and so on. So it's a large ecosystem, and let's say like it's not always working easily together, but most of the time things are working pretty smoothly. Definitely much easier than hand encoding everything in the different tools. Yeah, last but not least, we use SBML sim for simulation. This is, I would say, like a wrapper around libroadrunner, which allows to do the things which we're typically doing with our physiological-based pharmacokinetic models, and do things like scanning and parameter fitting and so on. I would say this is more like this is very experimental. People can try it, but this is more like I would say in-house. The other tools I presented, this is I can highly recommend to use them. SBML sim will probably have more issues than fun with that, but feel free to try that. Yeah, short advertisement. As an intermediate, we always have internship projects. We're doing this online. This takes normally around 3 months. And if you're interested in develop physiological-based pharmacokinetic models in SBML, using standardized data, these tools, using libroadrunner, you're welcome to just apply. Normally we can't pay anything, but if you have like summer holidays and are really bored and have a few months and are interested in physiology and so on, you can definitely develop such models. Okay, so far so good. The remainder will be more practical. Yeah, I want to show like a few examples how we normally create such models and yeah, how we interact with them. First, I want to show how we communicate our models. If we like for instance, for the IDG model, if we publish something, we now create a Git repository where we version our models. And so, so we have different releases, and normally we try to document the changes between in release notes between the models. So for me, the model is not a final version, but often you find bugs or you need a new model version for other applications and so on. So we now really try to track our finished models, the SBML models in a repository. And yeah, you can very nicely then directly link to the SBML for humans report. And if you click on that, then yeah, it takes a few seconds. The model, which is now in the Git repository, by a simple web page, you can directly open this in the report. And in this report, you get an overview of what is in the content. For instance, here, this was this model I showed here in the beginning. It's basically this model, but now in SBML. Yeah, and you have different compartments and can annotate what do the things mean, like what is bile and what foul bile and so on. And this helps other people to better understand the model. What I find really important when working with models, you already can see these models become pretty big. You have like, I don't know, 50, 60 assignment rules and yeah, 16 reactions and so on. Yeah, normally they get much bigger. This is a simple model still, but yeah, you can easily filter for things. Like for instance, if you're interested in foul bile, where is it appearing in the model and so on. This helps you basically to find bugs, or like also to, if you see the model for the first time, to investigate what is going on with a model. Yeah, so this is normally part of the workflow that we yeah, add this models to a repository, and then we, depending on the model, we have different releases, and then you can normally make a diff of what is happening, and we document also what is going on with the model changes. Okay, this is basically if we have the finished model. Now I want to demonstrate how we create these models. Yeah, this is in yeah, I have a few tutorial files I will show, and if you're interested in these files are online, and you can just clone the sbmlutils repository, and then have a look at the examples which are in the source examples folder tutorial. So I will basically go a bit through this examples, and there's also an example of this ICG model, how this is created, and this can be seen here. So if you're interested in to learn more or try it yourself, what I'm showing now, all the files are here. Yeah, I want to start demonstrating how we create a minimal model, normal in sbmlutils. So this is a Python file, and yeah, you probably created already antimony models, and this is basically a string, and you can also interactively create that in Visual Studio Code. Here, this is basically a Python object, an instance of this model class, where you then set fields which correspond to the objects which are in the SBML information. And so normally you set things like SIDs, compartments, species, parameters, and reactions. So in the simple case, we just create a model which consists of one compartment, the cell. We add two species, S1, S2 in the cell. We add parameters K1 and a reaction J0, which is converting S1 to S2 with a simple mass action kinetic. So this is all you have to do for a model. You can set much more, but this I would say is a minimal working example. And then you call a create model function, which is basically taking this model, say where should the SBML file created, and then you can have some additional options for validation. Yeah, in this case, I'm just saying, okay, we don't want unit validation because we don't have units on this model. But otherwise, if you wouldn't set this validation options, you would also get your unit warnings. And then in the end, we have a function which allows us to visualize this in SciSBML. Yeah. So if you create this function, we get basically a bit of report here, which is showing warnings. And these warnings are basically, I would say most of the warnings are best practice. You should set a name, you should set SBO terms. Yeah, but normally everything which is warning can be ignored, but it's more like I'm giving, like, in my personal experience, if you give a lot of warnings, at some point people get annoyed by the warnings and they try to fix the warnings. So it's like, or at least my students are doing that. And so at some point the model quality goes up if you just have the warning, okay, this could be improved by doing that and that. And by being specific with this warning, and it allows also like to easily update that. For instance, here warning name should be set on parameter K1. Then if you would now set a parameter here or an SBO term, you would just say this is weight constant yeah, for J0. You can add that or add an SBO term. And in this case, this is SBO. We have to, in this case, this is really a very simple model which only has a factory. If you want to work with metadata like SBO terms or other ontologies, you would just import also the metadata, and then we get simple code completion. Yeah, and if you don't know what SBO term, most of the time, if it's not a KM or a Vmax, then I use quantitative systems description parameter. I don't know, probably there's something better, but I would say this is yeah. There's probably also a weight constant or something like this here. I'm not sure, mass action rate law. Yeah, but yeah, you get direct access to the parameters, but sometimes it's a bit difficult to what to choose. I would say anything is better than nothing here. And then if you would just recreate the model, you can already see you have less warnings on here. What the visualized SBML is doing, this is I would say yeah, this is just a helper function which is automatically loading the generated SBML model in SciSBML. You have multiple views in here. I would say there's a space view, which is just giving you the species reaction graph. And we can see here we created the S1 to S2. And yeah, we can also look at this all graph, which is giving us more information. And we see basically how are all the SBML objects connected. This is, I would say, is helping a lot in debugging and figuring out problems. Because often if you create SBML models, the parameter is just in the wrong reaction or like crazy things, or parameters are not connected. And you see this very easily in the graph. And you get also a feeling what is connected to what. We also have ports in here. This becomes important later in model coupling. Ports are a concept from this hierarchical model composition in SBML. And you can basically indicate what are interfaces of your model if you want to couple your model to other models. And so in this simple model, we also added two ports, a port for the compartment by setting the flag port true. And we created a port for the species S1. And we will use this for coupling later on. Okay, but I would say this is the basic usage. You just create your SBML objects, add this in here. Yeah, you should have a bit of knowledge of SBML and what you want to create. And then it's pretty easy. Yeah, I can highly recommend reading the SBML specification if in doubt, or looking also at the libSBML library and API documentation. But yeah, but this is definitely a programmatic way to create SBML, and I would say it's a bit higher level than writing antimony models, but it also allows more flexibility. And this more flexibility is basically you have a real programming language where you can manipulate things. And this is, for instance, if we want, yeah, I would just show this linear chain. So you can easily create more complex models programmatically. Like for instance here, this looks already very similar to what we had before. Yeah, we create a model, we give an ID, and then we just set a compartment in the species. But now we can programmatically add objects to our model. Right now we have only a cell and a S1, but we want to create a linear chain of things. So we can just basically use a loop, and in a loop just add the additional species we want. add additional parameters and add the additional reactions. So what we're doing is we just create a linear chain out of 20 additional species and reactions and connect them all, and then yeah, you can very easily in a few lines of codes also create like more complex models. Yeah, you can see this here in the if we create that, now we have a nice nice long snake of species and so on. Yeah, so I would say this is the biggest strength if you have to interactively manipulate things. Like I said, a new feature is now that we support antimony. So basically, if you have your model as an antimony string, you can now basically visualize antimony models. This could be interesting for people. Basically, if you don't want to manipulate your model, but just visualize it and use this to inspect what is going on in your model and so on, sbml, you can just use this visualize antimony function. Or, of course, you can do things like just load the model now in the internal model instance, and then do more complex manipulations, like for instance setting annotation and so on. And I could imagine this is also if you have like things which are easy in antimony, you would do that, and things which are more complex, or you want to have like repetitive things before you start like doing repetitive string concatenations and stuff like that. Perhaps one solution could be just load your antimony core model and then manipulate what you have to manipulate here in Python. Yeah. In this simple case, we just basically we take the this is an antimony model of the repressolator, and what we do is yeah, basically we add an additional species, this PA, and we set annotations on our species. For instance, if you have repetitive annotations and things like that, this is, I would say, more easy in a programmatic way. Yeah, and you can see basically what we do here. This is just the yeah, we basically define the repressolator in antimony, which is negative feedback cycle of 3 proteins, and yeah, we just visualize the model. So there's a one-liner if you want to do that. And the second thing is we now added the species and added annotation, and this is just our second model variant. We just added the species in here. It's just proof of principle. You have this as an internal model, and now you can do everything you want. You could set SBO terms and so yeah, feel free. Everything which on the normal model objects is allowed is allowed on this imported model objects. Interesting things I often use is model composition. This is basically a hierarchical model composition with the comp package is sometimes a bit complicated because you have to define interfaces and you have to link things and you have to put things in a top model and so on. So I would say there's also more like low-level model merging, which is just you take all the objects you have from one model and you want to add all objects from another model and have a bit of strategy to resolve conflicts and so on. And this is basically this second way of merging models. You just provide in the create model a list or an iterable of model instances. And then in the order of the model you put in, it's resolving the SID conflicts, if this makes sense for anybody besides Lucian, I don't know. Yeah, but things like that. And then it puts all the objects together in one flat model. So what we're doing here, we're basically just importing the model which we generated before. This is also nice if you have like the whole thing, the models as Python objects, you can just import them and reuse them very, very easily. So in this case, we're just importing this minimal model which we created before. And now we create a second model, which has just a parameter K2 and a second reaction, which is using S1. And you can see we're not defining the S1 anymore because the S1 to S2 was already defined in the minimal model. And then if you put this together, we get basically a more complex model where we have the S1 to S2 with J0 from our minimal model, and we added an additional production term here to this model. This can be also interesting if you want to have driving functions or simple, like basically I would say things which are driving certain things in your other model. This is a nice way to compose that and provide input without going to hierarchical model composition. Okay, what else do we have? Yeah, this is the random network. It's just an example also like of the of this whole idea of creating things programmatically. You can of course also just randomly connect things and then create a random network of nodes. Things like that. I'm sometimes, I would say some of this functionality I'm using basically for benchmarking and testing. Like for instance, with this linear chain scripts, you can imagine you want to just test your simulator or your tool, how it is performing on increasing length of linear chains by increasing sizes of random networks with a certain node degrees and so on. And this is easy then to just programmatically just create a whole bunch of test models for certain things or certain applications and test performance. So this is definitely one thing I'm using that for. And then you can easily create random networks of different size. Like for instance, you can just use small size or like many species and not so many links, and then you get a respective very sparse graph and so on. Okay. One important thing I'm often doing is model annotation. And I'm having my annotations often separate from my actual models, and this makes sense because I often reuse annotations. One can imagine with this whole body physiological model, I don't want to every time I create a liver in any submodel to redo the annotations, but it's more like we have a database of, okay, if you have something called liver, this is the annotations you should put to a certain model. And so we store these annotations a bit separately and then use them to annotate things. In this case, there are different ways to define it. You can also define it in a Python module. Sometimes we define this annotations just in an Excel sheet, and then we map based on ID patterns on our model. And this pattern matching allows really to annotate also a bunch of objects. Like for instance, if you call everything starting with KM, a KM value, you can easily just annotate Michaelis constants in models and things like that. So there's like this, I would say, pattern matching, plus you have like naming conventions for your IDs, allows with a few lines just to easily annotate your model. And then there are different ways. Either you have here, for instance, we have the annotations in a separate file. We have our minimal model in SBML, which we already created. And then we just say, use this annotation in this file and add them to the model. And in this case, we still get this minimal model, but we can now see that, okay, it's very small, but you can see you have annotations to the S2 is annotated to an SBO term. And then you can resolve. Oh, okay, this should normally resolve. I clicked on the wrong, sorry, I clicked on the wrong link. I clicked on the SBO, but this should normally resolve to the actual link. Oh, strange. Okay, I have to test that again. Yeah. Okay, but this is annotations. But we could also look now at the annotations in this SBML for humans. So we created this annotated file. Perhaps I want to show like how to use this also if you have this on the hard disk. So you would just load the created file. In this case, we created this minimal model with the annotations here. And then we can load that, and we annotated that with these SBO terms. Like for instance, we put the diglucopuranose and the simple chemical on the model, and then we this is nicely resolving here in the not so nicely inside SBML. This should basically show the same things, but this is the core idea. You just add a few simple terms which you can define in an external spreadsheet. For instance, here we defined basically the diglucopuranose. It should map on the S1. And then you can easily store your annotations somewhere else or in a database, or I don't know. but I think this is a good idea to separate annotations from actual models and then have some scripts which bring this this together. And I think this works also nicely with antimony and which is more like for the model creation, and okay, which is more for the model creation, and the interactive things here, or the Python scripts can automatically put the annotations in there. Okay, so I just have to check. Probably this. Yeah, probably I killed it. Do you still hear me? Yeah, I think I killed my tool. Okay. So okay. I think the last example I wanted to show is really this the ICG. The ICG model which we created to just show, okay, this real world examples, they don't look so much more complicated than what I showed here. And so for this ICG model, I said before, we basically have a whole body model and we have a liver model. And if you just look at the liver model, this is basically it's not very complicated. It just has yeah, very similar to this minimal model. It has like some units, and it has some compartments. In this case, we just have the external compartment, the liver, bile, and feces, and then we have some species which we put in these compartments. We have some reactions, which are basically the importer, exporters, and so on. And yeah, in the end, some transport reactions which connect everything. If you then look at this, if you look at the simple model, yeah, we see this is very similar to this publication figure I showed. Yeah, we have also programmatic ways to lay out these things, but what I'm often doing if a model is finished, and I'm just creating a layout, and then I'm storing the layout information, and then I can easily just load it and apply it. So in this case, this is basically the layout for the model, which looks very similar to this publication figure I showed before. On the other hand, we have the body model. This looks, of course, now more complicated. This has just much more objects in it. It basically has a lot of compartments in the end for the different organs: liver, lung, venous, arterial, plasma, and so on. It also defines like the mapping of the external models. In this case, we have one external model, this liver model, which we want to couple. And then we have yeah, a lot of, let's say, like a lot of definitions and repeating things and programmatic creation of, okay, for every tissue which is not a blood compartment, we want to do that, and things like that. It would be very cumbersome to type this out, and so here you can do very easily like things like, okay, if this is this pattern and not that, then create that and reuse this IDs and things like that, which is for larger models really becomes really important. Yeah, we have replacements for the hierarchical model compositions, and yeah, in the end, I just want to show this is much bigger. We have a lot of parameters here, assignment rules, and yeah, I just wanted to go to the reactions and just show most of the reactions which are in here, and the transport reactions which transport between the different organs. And there are simple reactions which are just taking, okay, the blood flow times the concentration in the one compartment and then put it to basically to the next compartment. So there are just a lot of these reaction flows in here, and depending on the connection in the physiology, we have to create this model. Okay, if you would create this body model now, this is let's say this is a bit it's a bit boring. It's basically a large spider network which is connecting the different organs via blood flows. The lung is going in the one direction, and the rest compartment and the liver and so on going in the other direction. So this is pretty boring, and we don't have any metabolism in here. You can see basically the substance ICG can just go here in the liver, but nothing is happening. And this is because in this model version, this is just the whole body without the liver, and so we can develop these two models separately, and then we basically have the coupled model, which is just combining things. And how we combining things is most of the time here via such a factory. And what we're doing is basically we creating the tissue models. Here you can see also like now we can very easily import our submodels, which we have, and we just say, okay, in our script, now create our liver model. And here we also creating an omics archive and storing the model directly in the omics archive. Then basically create the whole body model, store the whole body model in the omics archive. And then we're doing a flattening procedure and say, okay, now create the flattened model and put the flattened model also in the archive, and then store everything as a combined archive and print the content of the archive. And in the end, we have an additional script that says, okay, create everything and then visualize for all the models which are in the archive, visualize everything. And then what we get is basically a combined archive where we have all our models stored, and get an additional flat model, which is now the combination of the liver model with the actual whole body model. I'll just load the layout. And you can basically see that we have here the coupling now, and they are basically coupled via this ICG species, and then the additional transporters are coupled in here. I would say this whole body physiology is really nice for the coupling, because most of the coupling interfaces are very clear. These are species which are transported in the different tissues or in the urine, feces, and so it's pretty easy to do the separation in the hierarchical model composition. The combined archive can also be loaded in this SBML for humans and to look at the report. I would say this is basically the workflows how we create models. And I would say for small models, if you have a handful of species, antimony, things like that, Comparsi are really good tools. As soon as you go to larger models and have to create things programmatically, I think a tool like sbmlutils could help you a lot. Also in creating test models or extending models, merging models. I think these are typical things I have to do with models, and this is a lot is possible in antimony. A lot is possible also in Comparsi, but often it's if your use case is not covered by the tool, then you're often like a bit alone. And here you, it's difficult to fix it. Let's say it like that. Here you more like, okay, if you can program, you can find a workaround and compose things so that you get in the end a valid model. Important thing is also unit validation. Perhaps I want to say a few more words about that. So if you look at here, like for instance, at the liver model of ICG, if you would just use wrong units, we would just immediately get warnings. And especially for the larger models, we really need the unit validation. So if you would have here something like millimole, basically directly get a warning and see, okay, your model still doesn't have any errors, but you definitely have a problem in this kinetics, which is not balanced, and basically your kinetic laws don't produce consistent units anymore. And so in the end, it's basically okay. From this error messages is often pretty simple to figure out what is going on. Also, what I find pretty helpful, it's giving a lot of information if things are just missing or incorrect, because often things are missing. So so by having these objects, you often get, okay, what are required things, and it's very easy to figure out, okay, what is the problem and what is still wrong in my model. Where with other tools is often like a bit of okay, if you know what is wrong, it's either you know what is wrong or you don't know what is wrong. But it's difficult to inspect things, and here you can really have a look and Okay. I think I stop here to have a bit of time for discussion. Thanks a lot for the attention. let me know if you have any questions.
Thank you so much, Matthias. I know we had a couple comments from Herbert in the chat. I don't know if you want to ask him.
Yeah, I guess. Yeah, this really looks really great, Matthias. So one question. So I had one question: whether you could load in an antimony model and then dress it up with all the extra information. The answer was yes. After I asked the question, because it's probably quicker to generate the model first in antimony, then load it in, and then add all your extra information.
Exactly. I would say this is it depends on your typical workflows. If you work a lot with antimony and you basically have a small model and now you want to add something which is difficult to add in antimony, or you, for instance, you have your antimony model and you want to just create an area of that or something like this, this could be a use case for this tool. There's this sweet spot between, okay, you type a few lines in antimony and okay, now I have to go to something more programmatic. And by this antimony import, this new feature implemented today, I thought like this is what I often have. Like often I think this is to overkill, and it would be nice to just have two antimony lines and then do the rest here. And I think this is this could solve a few interesting use cases.
The other question is, you notice there on your line 131, you have names for the SBO terms. Are those you provide those names, do you, in your software?
Yeah,
SBO simple chemical, for example.
Exactly. This is basically this is a package by metadata, and what it's doing, exactly in the background, and it provides like this classes with lookup for ontologies, and this works for small ontologies very well. And I provide this for SBO, for the evidence ontology, and for Kisao. The problem is, as soon as the ontology becomes very large, this lookup, suddenly all the tools break down. If you have like an auto completion of, I don't know, 1 million Go term, and then suddenly the basically the Visual Studio Code and the PyCharm and so on break down. So for SBO and Kisao this works. My initial idea was like to just do this for all the ontologies which we typically use, like KB, Uniprot and stuff like that. But this just like the one thing, it became very slow, the lookup. On the other hand, so the import became very, like if you import something which has million of fields, it basically your import suddenly takes 20 seconds. I don't know. This was like it solves it solves this SBO Kisao things, which are very nice also for ZML. I use the Kisao a lot. But for really using real ontologies, this is unfortunately not a solution.
Yeah, because all these identifier numbers just doesn't, I don't know, just doesn't work. You need something like this.
Have you considered using a stripped down ontology from Kevi or something for like things that we use in our lab? And then slowly add to it over time as people need more things?
Yes, this could definitely like about the NCBI taxonomy. I basically did something like that, cut out all the 5 billion bacteria, just use normal species and just stop at the branches, stop at E. coli, and then don't care about all the strains.
All the sub ones,
down. This is a good example where this approach worked. With Kiwi, it's more difficult. I could basically this adding as you do it could work by, for instance, like just passing all annotations which are currently used, like for instance in biomodels or in typical models, and then just build a stripped down version of that. This is a nice idea and could work.
So one last question for me. Is there any way to attach experimental data to this?
What do you mean exactly with that?
Well, maybe at least associate data with a model, so that if I give the model to
like
somebody else,
they
get the data. They get the data as well.
Yeah, we have something which is called interpolation.
I mean, for example, time series data. I mean, we've got time series data, right, for the signaling pathways, and we'd like to associate it with the model.
Yeah, this is definitely
So-
working. What I'm doing is basically, I call it interpolation. I'm just
Yeah.
loading the data, and then I provide the MathML for either linear interpolation, spline interpolation, or just constant interpolation.
Oh, I see.
And then you
Yeah.
basically load the data, get the MathML for the function, and then you can just add it easily in the model. Not well documented, but I'm also using that a
Yeah.
lot to just drive my model with experimental data. Yeah, I
I mean,
can
we have a use case maybe for this. Maybe we need to get you to talk to the cancer group we have about your tooling. Could be really useful. This is also something we should help with with the center as well, because this is really nice class. So
yeah, yeah, definitely this driving with experimental data, it works.
yeah,
One thing I really like about this is that I can have a nice diff and diff of my model changes, because the
Yeah.
diffs with the SBML with SBML XML are very bad.
yeah,
Well, it's very difficult to work with them. There are some tools by the Greifswald group and so on, but it's all complicated to use and doesn't help you
Yeah.
on GitHub. And
Yeah.
here, so I often don't even store the actual SBML. I'm just storing the scripts which can generate the SBML.
Oh,
Then I
yeah.
get nice diffs. I basically just see, okay, I changed
Ah.
this 5 lines here to create it.
Yeah.
And this is also for me nice to have
Okay. Yeah.
see what is wrong, or what. Often I break the model and then I can just do a git changes here, like just look at the local history of my model, and then I can just see, okay, oh, well, what did I do? And here I did this
yeah.
nonsense change and so on and so on. So this is really nice because this is also directly in the you basically have more model provenance via your git commit history of the files.
Oh, yeah. No,
So
right,
yeah, there's lot
you
of
see that
things.
code there you've got in front there now, that code there. If I were to, can I convert an antimony model into that code, which I can then edit afterwards?
Yeah, exactly. This is basically what I showed with this model antimony file. This is basically what this is doing. This is loading.
Yeah, but then I'm using methods to add things. I don't get the actual raw code that you had in the other page.
No, I know what you mean. This
Yeah.
What in Tellurium, basically writing everything out to a Python script again. Yeah, I don't have that yet, but I was really unhappy with that in Tellurium also. But I don't know. Yeah, perhaps I will provide that. This shouldn't be too difficult, but yeah, it's more like if I have users requested and you really need that, then I can implement it.
Okay. Sorry, I
basically be an SBML to the dictionary form translator, right? Essentially.
Yeah, it's a question what should be generated. If really the model generation code should be generated, something like this model things. Yeah, this is it should.
It should look like that. Yeah.
Yeah, it shouldn't be too complicated. The problem is like with the nested things. Like I didn't show too many nested things, but the problem is the problems really arise because everything is an S space, and on S space, certain things can extend S spaces. Like it's mainly the annotations, but also like now like key value stores, uncertainties, things like that. And so you often have objects which can have all the sub objects and so on and so on. So this whole thing is in principle like it gets nested and nested and nested. Yeah, nobody's using things annotations on I don't know, on a flux objective value. I don't know, things like that on this really small items. But basically to support it, this becomes really complicated. And this is also with this automatic code generation, this becomes a bit a lot of things are just becoming nested and recursive, and this is.
No, I see. Okay.
Yeah. But yeah, in principle, if people want this, I could implement that. Just open an issue for that, and then I'm happy to address that.
When things get put in the issue tracker, they just magically happen eventually.
Exactly. This is for me. Yeah. At some point, if I have time and I see, oh, there's this issue open, then I'm addressing that, and often the issues users have are very similar issues to which things I have, or they solve different problems for me, and so often this is very useful to implement things like that.
We maybe have one question from anyone else in the audience. Just wanted to check in. getting close to the end of the hour. All right. Well, thank you so much, Matthias.
Yeah, thanks a lot. It's always
Sure.
fun giving talks here. I hope I know at least Lucian and Herbert, like, they enjoy what I'm doing. I hope it was not too technical, but I think the idea is also to show like some real world examples of how these things are applied, and
Yeah,
not only
exactly.
the toy models but this, like SBML and a lot of this tooling just scales up. And if you want to do big things and big projects, this works, and this is also very nice.
Good.
I'm sure some of these tools will make it into the summer school next year. They always kind of slowly creep in. Yep. Thank you so much again.
Thank you.
Okay.